PhDs and also published more than 100 articles in different leading journals and conferences. I invite Dr. Nandakumar to give the presentation. Thank you.
Hope that I speak with proper modulation. I hope that I speak with proper modulation. Means you are hearing it properly, right? Because I am not doing this business with science and technology for the last 3 years' time. This institute, it financially supported me for 25 years. My family depend on that. And for the last 7 years, this institute give me pension and let me live. So I'm loyal to that. The moment Dr. Madhyarajan called me for the talk, I told him yes. Then he spoke to me, sir, speak something on what you have been doing here. I told him, yes, I will do something with finite element method. That is the only thing that I was exclusively dealing with here, right? Structural analysis and other things. So usually when we speak about structural analysis, people always prefer to assign 2 words, linear and static. The moment you speak something on non-linear, the moment that we speak non-linear or dynamic, we say that there is some sort of a complexity that has been added to that. I had a professor in IIT Madras. He is a Tamilian by language. He will say it like this: there is nothing called non-linear. That itself it is non-linear. That is, I am linear. Right? Because you require a linear analysis if you want to proceed to the non-linear analysis. You want a linear analysis, you want to go to the buckling analysis. So it's a very basic requirement. So what I will speak, maybe 30 or 35 minutes, it will be on a time frame. I am speaking on structural analysis, the past, the present, and the future. It is something in the time domain. Right? So don't think that it is something complex. I don't have any equations. I don't have any figures because I left them long back. I still remember in one of our aerial conferences, Professor Kundu came and he gave a very talk, something that was 25 years old on the Panama Bridge, Panamax ships. So it is something like that. Anyway, Professor Kundu is a very honorable professor and he is very much ahead of me in that. Right? So when we speak on marine structures, I start from the basics. We generally classify structures in such a way that, depending upon the location, you can call it, where it is located. Say on land, offshore, coastal, near shore, and ultimately we will call it, say, many things together as marine structures. Right? So the very purpose of structural analysis is to the qualitative and quantitative estimation of deformations, stresses, and deflections. And many times we go for estimating the ultimate strength, the residual life, and especially to the marine aspect on predicting collapse. Because the moment that you speak, it is something marine. You think about the ocean or the seas, something subsea, there is an external pressure, and there is a collapse. Right? So when you look into the marine structural aspect, so very maybe from the beginning you can call it, only the floating structures were there. And many times your analysis or design, structural analysis or structural design, that very much dependent on the observation of the behavior of the structural component. It may be from a single log piece on which the first primitive man traveled. From that case onwards, it was something that used for based on the observations. And the ship structural design was based on the empirical equations and thumb rules. And the rule books in the original days gave a good narration based on the experience on board about this aspect. So it was more on the empirical side, experience, and based upon these things, a set of equations are given in the rule book for the structural. That is what your moments are for the design, what your shear forces are for the design, like that. So I am speaking about the past. That is the one that I spoke was something what you call as the primitive. Now coming to the past. For the prehistorian, to that we speak on the historical aspect. So the developments in the theory of velocity achieved through the mathematical tools, beginning with the procedure operations of rate of change in the form that is the Newtonian calculus, differential calculus as dy by dx. It brought so much theories into the structural analysis, basically. You are applying the force. Then the first item of rate can be with respect to time, what you are doing it, the rate of loading. You are applying the load on a finite area, then it comes so much load per unit area. Then the first quantity, the first emotional expression by the structure is the displacement. You go for the rate of change of that. You are moving into the velocity part, acceleration part, then the force part. So the mathematical background that is given by basically from the Newtonian calculus, that is the only aspect that I want to speak. That gave rise to so much of equations and theory of velocity, what you call it. That is how the applied load is getting dispersed down a deformable medium. So the first order, second order, third order differential equations, which the solution obviously brings certain constants into that, what we call it as the material constants. So it's an entire drama that is very much existing. So that is based upon, so the differential equations based on the theory of velocity was served as the pulp for generating the structural analysis part. Then what happened is, so that comes from the mathematical side. The mathematicians did it. The engineers are a different category. They want to resort to the design aspect of it. They want to see how much thickness is there, how much depth is there. So that made them go for assumptions based upon the physical reality, what we call it as the strength of material assumptions. The examples are, if you want the column buckling load, you have your Euler equation, which is derived from the second order or the fourth order differential equation relating the moment and the displacement or the curvature. You have the Bernoulli's equation for simple bending. Once again, the load, the rate of loading is shear, and the next derivative is your moment. That type of relation. You have the Kirchhoff equation. I'm sorry that one H is missing there. I'm very much sorry. There are 2H and 2A for Kirchhoff. So the Kirchhoff equation, the fourth order plate equation for the bending aspect. Then the Hoop equation for the stresses in the cylindrical shell, etc. like that. So this is what I mean by the strength of material assumptions on theory of velocity equations. You are getting things in a closed form and a final form, and the approximations are not numerical but conceptual. Right? So what happened is, this World War I and II boosted the structural engineering research. For example, all the closed form solutions given in Timoshenko's book, Theory of Plate and Shells, was sponsored by the US Navy. At the end of each table, as a footnote, you will see that This part of the research is funded by the US Navy. So the war supported structural engineering, funding for the structural engineering. So along with the development of numerical solutions, differential equations like series expansion. So here comes the numerical part of it, where you have got sufficient scope for approximating the value to the level of your desire, to the level of what you call as the engineering accuracy. So such equations were further developed. And one of them has been the finite difference method, which gave so much impact or so much support from the aeronautical structures, basically from the Boeing company. Many names are there like David Bushnell, etc., who made extensively on that. Even at the Bushnell's period, that is 1970s, they could advance the finite difference method to composites. They could do that. The finite difference method is as simple as putting circles, but it is as difficult as assigning the phantom nodes. So I prefer to make this time, that is 70 to 20s. We will call that the present situation, because during this period, there is only one tool that has been used for the analysis. I'll come to that. So the application of the finite element method made remarkable achievements in structural engineering. The involvement of the finite element method, or the involvement of the scientist or the analyst having finite element method as a tool into the structural analysis was so much so that there was nothing that was unachievable for the structural analysis. You define the structure, you define the load. Here is the answer. With so much of confidence, the entire structural engineering community in the world could speak on that with this particular aspect. And in this context, I just want to make, say, two statements on finite element method. If you ask me, what is the strength of finite element method? The answer is just two slogans. One is, finer the mesh, better the result. Finer the mesh, better the result. You want a better result, to refine it. The other is, what is the second one? Finer the mesh, better the result. I think almost 50% of the community I taught finite element method. It will be a disgrace on your teacher if it doesn't come to your mind. The second aspect is the interpolation. You go for an interpolation function which serve the 5 C conditions. The 3 from the convergence and the other 3 regarding the stress aspect. You are going to get the exact result. So the interpolation and the mesh refinement, they are essentially the strong aspect of finite element method. And it survived, say, over the years and still surviving with changes. Right? And another thing is, this mathematical trick have been in use, say, starting from 1940s, but only with the advent of the numerical computing, that is the efficiency in the numerical computing, came up to that level that this method became popular. So if you ask, what made finite element method popular? The answer is the electronic computing, the digital computing. That is the answer to that. Because there is something specific I want to speak, maybe in the last 5 slides, this particular aspect. And how this is related to the marine structural engineering? Is it something basically for the structural engineer or not? It's a very simple thing. There is something called the Kawai beam element, something developed in the 1970s. So this is exclusively made for ships, mainly for the analysis of the container ships. Container ships are open structures, involved open structures with, one end is not closed. So it absolutely the torsional rigidity part is something very low. The J part is something very low. The GJ becomes very low. So ultimately it cannot take that much torsional load, the torsional rigidity aspect. So the analysis for the torsional loads of the ships are generally a big problem. And in that, this particular element came into picture. That is, the U, theta, and omega could be calculated using the Kawai element. U means the axial deformation, that is your P by A or PL by A type of thing. Then theta is the twist, that into L give you the other part. And omega is the warping. That is how much it came out of the plane, cross-sectional plane. So these three quantities can be coupled in the Kawai finite element stiffness matrix. All these 7 terms are filled up in the first row. It is fully populated, so that you get always the coupling of the values. That has been the advantage of Kawai. So the argument is that the first major development in structural analysis using finite element method, it was something meant for the ship structural analysis, precisely. So as we progress on that, the force estimation is something very critical for the marine structures in general, especially for the floating structures, ships. So the wave force estimation, it has been tailored into the ship structural analysis with the support of the computational fluid dynamics, incorporating statistical and spectral representation of waves. Then there is a semicolon. Besides, the displacement stress output can be obtained in the same format. We call it spectral analysis. So the spectral analysis capabilities have been injected or tailored into the finite element method, or otherwise, vice versa. And it came into the use. So moving into the offshore engineering part, that is the retrieval of the hydrocarbons from the seabed. We have a boost to the offshore engineering, especially starting from the first Iran-Iraq war. The hydro medium made the structural analysis complex. That is, your structure is founded on the seabed. You have got a water depth from the bed to the free surface. Then you have got a structure protruding out into the atmosphere. So that particular water medium creates all the issues. The wave loads, the current loads, the cyclic loads, all these things. The offshore structures are mainly employed for the production, storage, and supply operations. Right. Then there is a major class of what we call the subsea applications that include the subsea vehicles, water atmospheric pressure chambers, storage structures like that. Generally shell structures, maybe cylindrical, spherical, conical, or combination of these things. And all these structural analysis problems, FEM has been finally adopted as a tool, almost. I mean, it is accepted. I mean, something like a democracy where there is no opposition. You can call it like that. All pervading. The structural analysis of for marine structures generally cover, that is, these 5 factors are something that makes totally distinguished from the onshore structural part. That is the response of the structure for the torsional loads. Because many sitting here with the naval architecture background, to them it will not be a surprise. But for the other engineering community, it is a big surprise. When a 300-meter vessel is in the sagging condition, you are dealing with a cantilever beam of 150-meter span, which means 50 floor, 50 floor, which occasionally may be 1 in a lakh structural engineer may come across in the design aspect of that. When we think about a large container ship, a 20-meter by 10-meter hatch opening, hatch cover, falling through a height of maybe 15 or 20 meters, due to the hatch diagonal elongation when it is facing a quartering sea, the other structural engineering community cannot imagine this. It is beyond imagination for them. So that is why I speak this the effect or the influence or the response the torsional loads on the ships in general with an open format. It is something very crucial, critical, which never comes into the purview or the jurisdiction of any of the onshore structural experts. The other is on the aging and the risk. The other is on aging and the risk. If you have a concrete structure onshore, you say it has got something like 60 years of life. Especially when we deal with the steel structure, and in a very corrosive atmosphere, aging creates a problem. and risk otherwise, especially with the failure, collapse, all those things. Something very serious considered to what is there on the aspect. Then the corrosion. Corrosion means the loss of thickness, the loss of material, loss of strength, which further goes to the aging, that is augmented aging, and then subsequently to the risk part. Then the collisions. Ship colliding with another ship at various locations, various parts on the hull form. Ship colliding with an external object, things are different, and that give rise to the forensic analysis. A conventional structural analysis differs from a forensic analysis, mainly in the sense that the forensic analysis you are doing is on a real structure because the accident happened to the real structure. Whereas the analysis has been something there for the hypothetical structure. For example, when you think about the, say, maybe the collapse or a disaster with a gas capsule mounted for the surface transport, it is supposed to be a perfect cylinder sphere combination. But in reality, it will be having so many dents on the surface, imperfections, and subsequently reducing the strength of it. Then the fracture aspect, because the fracture is so critical here, starting from the Titanic period onwards, for the marine structures, that the fracture directly has got an impact, you cannot separate out fatigue and fracture. Then this fracture, subsequently, it goes to it badly influences the corrosion aspect as well, right? Stress corrosion, what you call it. So all these things, make the marine structures, generally complex. But still, the aspect is, with all these difficulties or complexities, your finite element method could propose a solution to the analysis with all these issues. All powerful. So the marine structural behavior differs from the other conventional structural behavior by virtue of, say, the heavily stiffened thin plated structural pattern. The major issue is how the load that is applied on the surface of the plate is shared between the plate, the stiffener running in one direction, or the stiffeners running in the two direction, the load sharing mechanisms. So that makes the issue there. The flexible and the rigid modes of deformation of the structure. When it's a floating body, you treat it as rigid and do some calculations. When it's a fixed structure, you take it as flexible and go for the calculation, something very logical. But there are situations when, for a floating structure itself, you have to look into the flexible modes. The other is the one-atmos mobile structures like submarines. Once again, the stiffened shell structural forms. One-atmos chambers for inspection. Their thing is that it is the openings are unavoidable. What we call as the unavoidable holidays on the structural surface. Because of the mountings that are very much there, that take away a lot of strength and aspect. Analysis is something rather difficult. Stress concentrations are very high, like that. Then the storage structures with thermal analysis requirement. All this LNG transport systems, etc., come in that category. And shells and other forms which get strength through the foam. As I told about the forensic analysis, the moment there is an imperfection on the surface, the structure loses its strength because the strength is gained by the foam, the geometry. Once you lose that, you are losing the strength. So, with even these issues are solved or solvable using finite element method. So the two aspects, one regarding the structural configuration, the other regarding the structural behavior of the loading. That is what the previous slide and this slide speak to you. Yeah. So moving fast, coming into the future aspects. The first part comes from the material and the form aspect. That is, the composite is getting so much momentum as a structural material in the marine environment. It is true that immediately after the World War II, we have started making composite boats, ships like that. It was at a, what is it, you can say that it was increasing at a decreasing rate, you can call it. But what happened later on, especially in the 1990s onwards, there is large involvement, or there is huge involvement, or there is wide involvement of composites as a structural material. And the issue is, it totally differ. What happened? So what happened is, the structural behavior of composites are totally different from the conventional material that we are familiar with in the design aspect, concrete, steel, etc. The failure patterns or the failure modes or the failure theories that we assign are totally different for our conventional material like concrete or steel and composites. So this material make an issue. Then the sandwich constructions and other that type of, say, modern, or we can say that is something that comes as the outcome of, say, period or time or technology, the various structural forms, so combinations of the material that have been used, etc. I think I am putting somewhere bad. Yes, yes. That so the changes in the various environmental parameters, changes in the functional or the operational environment, influencing durability and strength due to the change in wave climate. The change in the global climate, that is, generally there is a rise in the wave height. Starting from that, there are any amount of issues. The trend in the current are changing. The directional patterns are different, like that. And the changes that is happening, the climatic change that is happening in the environment, influence on the loads, the fatigue behavior, and the corrosion. So the loads the designer can account for, but the fatigue behavior nor the corrosion aspects, a designer cannot quantitatively estimate and include that in the design aspect. So it remains an uncertainty, or it remains a risk. And the changes to the new materials, especially the composites, the joining techniques are bonding and welding. Then the thermal metallurgical features of cementitious materials, mainly used for bonding. So the issues are like this. When you weld two pieces, they are melted and then taken as a single identity. There may be a change in the Young's modulus. There is a change in the stress level. There may be some amount of deformation that happened. But notwithstanding all these factors, the entire material, the two pieces that are joined, they behave as a single unit. There is no third identity, which even the weld fillet, you need not take it to that extent, though the Young's modulus changes. Whereas for bonding, it is something else. You have one piece, then a bonding matrix, and there is another piece that is coming on that. And many times, the load transfer mechanism is something on the surface. So the trend is, it is the in-plane shear like this or like this. That matters. So when you speak about bonding aspects, the in-plane components of shear, that seems to be the critical quantity to be estimated. Otherwise, many finite element software that we are using at present cannot estimate these quantities straight away. Many things will be absent, which means that you cannot make a reliable design based upon your finite element analysis with a conventional finite element analysis. Yes. So the same thing happens with the cementitious materials, especially with the electronic industry. The digital technology applications go up, the cementitious materials and their thermal and the material properties differ a lot. So the thing is, you require a lot of new constitutive models. In finite element analysis, the material properties or the material characteristics are reflected in the constitutive matrix, and you have to go for the various effective, powerful constitutive models. So then came the era of data analytics, artificial intelligence, and machine learning, right? So the data analytics have got a direct impact on the wave climate model, and it has been very powerful, and it has been extensively used, and it is very extensively and successfully used for making the wave climate model, right? Then moving into the AI and the ML part. For new scientific discoveries and engineering innovations. So I make a break here. So we usually speak, that is the industrial revolutions 1, 2, and 3. That was the original seed for making, say, what we call as engineering nowadays. A theory in science has been made into engineering and subsequently to technology. So the growth was from science, engineering, and technology. Science applied to make it engineering, and engineering matured into technology for the production aspect. That was the basic concept. But once the electronic industry came into the dominance, and when the digital technology took over from the conventional technology, we changed the pattern such that it is science, technology, engineering, and mathematics. That is the way it goes now, STEM, they call it. So when you speak new scientific discoveries and engineering innovations, means what we are making from science to technology, and then comes the engineering. Man did the work. Man made a machine to do the work. Then man made a machine and kept away from doing the work. Then man made a machine to make a machine. Man worked and did the work. He made a machine and operated that to work. He made a machine and kept away from that to make the work. And finally, the man make a machine to make a machine that will work. So the first part is that for the new scientific discoveries and engineering innovations, this much should be read in between. The development of the new scientific principles often lags behind the pace of inventions with the sheer volume of data. That is, you cannot, the output or the outcome or the real world that you are seeing, the real response that's seeing, which can be digitalized into the data, the available scientific principles cannot cope up with that. That is the situation. The sheer volume of data that are generated across the multiple spatial, temporal, and design parameter spaces. And these class of methods cover the large class of interpretations. It is not interpretations, it is interpolations. I'm sorry for the commitment. So the last part leads that, notwithstanding all these difficulties or the issues or the lag that you find in the technology or the application of that, to cope up with the changes, what the society or what the industry demands. The last part is that with these things, we can cover it with, and there is sufficient scope for a large class of interpolations. I told you about the 2 slogans in finite element method. If you manipulate with the interpolations, things can be cracked. So, in other words, the AI or the ML applications basically something that can be tailored into your finite element method, or the finite element method can adopt your AI or ML. All right. So the neural network can be designed and trained to approximate any given continuous function. So the word continuous function is something very important to us regarding interpolations. I spoke to you about the 5 C's with any desired accuracy. So the reasoning for the previous statement is given here. The basic for your AI or ML is the your neural networks, and it can be trained to make any continuous function with the desired accuracy. This support the future computational discretization technologies. I am with the second slide. I am assigning or I am reiterating the stand that AI and ML can go together with FEM or vice versa. So the realities are the scientific or the engineering problems are such that is the current. That is, it is not science, engineering, technology. It is science, technology, engineering. In that situation, the scientific or engineering problems are such that the abundant data but undeveloped or unavailable scientific principles. That is, lot of data but lack of scientific principles. The other is both limited data and scientific knowledge. Both are limited. And the third option is, third possibility is the non-scientific principles with uncertain parameters and high computational load data. So this is a reality that we are facing. So how to overcome that? So the concept of mechanistic data science, which leads to the machine learning process operations like deep learning and the hierarchical neural network. And the purpose is to process the input data, extract the mechanistic features, reduce the dimensions. So the word reducing the dimension is something very critical for the finite element method or any structural analysis problem. We generally call it cults of dimensionality, CURC, cults of dimensionality. A three-dimensional object, the moment you say that it is axisymmetric, it becomes two-dimensional. One meridian is rotated. If that meridian is just a single line, it becomes a one-dimensional problem. So this is what we mean by the real problem is reduced, or the cults of dimensionality is removed by the assumption that the behavior is axisymmetric. Something similar to that, it is there. So my statement of cults of dimensionality, it was there in finite element method 50 years back. It reappeared in the ML discussions in this form. The process, this leads to ML like deep learning, hierarchical and neural network, and the purpose is to process the input data, extract the mechanistic features, that is to generate the data, and reduce the dimensions, that is reduce the cults of dimensionality, remove it from the scene, and learn the hidden relationships through the regressions. The data is processed with the regression analysis and the classification and regression classification, and provide a knowledge database. That is the way the concept of ML that is adopted to the finite element process. This is the procedural flow that will be taking place. 5 minutes. Which slide it is? 31, 32. 35 slides. 4 more. It is proposed for the ML-based FEM with reduced models and deep neural networks, and the database generated by the FEM is offline, and the final solutions during the online stage, which result in the fast and the real-time solution. This is the way that it works. The system works on that. And the issues addressed there will be the online dynamic system control, or the issues at present that we can directly employ your deep learning process using with the finite element support are like this: the online dynamic system control, structural health monitoring, vehicle health monitoring, automated driving controls and decisions, online advanced manufacturing feedback, that is additive manufacturing, that type of aspects. So such issues can be easily be addressed by the mechanistic data systems, right? So the procedure is, you get the data from the finite element analysis, you prepare the data for the mechanistic format, train the system training the data for the system in the neural network, then train the ML model further, validate it, and you develop the model for the industry or the final product. Additive manufacture. That's it. And the thing is that you have to take care for the role of clean data and the automated supervision. So when myself or Professor Krishnankuti started computing, there was a fill in the blank thing. Computer cannot do dash. The answer is what the human brain cannot do. Expand, GIGO, garbage is in, garbage is out. So these were the objectives I think that we dealt with. So similar thing happens here. The role of the clean data, the word clean is understood. The GIGO is still valid. There the automated supervision, that is keep the man away from that. The thing will be done by the machine. Man making a machine to make the machine. Then one more statement I prefer to add, though it's not in a slide. This concept of neural network in finite element method, it has been highly promoted by Professor S. Rajashekharan, who was a professor at PSG College of Technology, Coimbatore. He has written a book long back, which has got a very exclusive discussion on this neural networks and artificial neural network, which give you a very, very clear idea for the structural engineering side. Very clear idea. Now, whatever comes in neural network is electronically biased. The other thing is rather physically or engineeringly biased, they can call it. So if anybody has got any old copy, look into that, resort into that. This AI ML trick for a structural engineer can have be solved with that thing. SR's book on finite element method, which mainly deal with the neural network. Okay, Jai Hind.
Okay, thank you, Dr. Nandakumar. Just, I think of any quick question because we are running short of time, which Dr. Nandakumar can answer. Anybody? Oh, okay, then what we'll take the questions maybe later. Yeah, thank you. Just give a big applause to Dr. Nandakumar.
I now invite the session chair, Professor Dr. P. Krishnankuti, to kindly present a token of appreciation and a certificate to Dr. C.G. Nandakumar. Sir, please.
Okay, sure. Moving on with the next presentation, I call upon Dr. Ganeshan. Dr. Ganeshan is with CSI or CCRI Karaikudi. And yeah, he works in the area of, he's a principal scientist at the Corrosion and Materials Protection Division of CSIR lab. He did his PhD in metal processing from Norwegian University of Science and Technology. And he worked in the industry for some time, and including Technip. And he also worked in another company in Norway. And he has published many papers in fatigue and fracture mechanics, metallurgy, welding, and laser applications. So I call upon Dr. Ganeshan to give the presentation. Thank you.
Good afternoon to all. It's an honor to be here and share whatever the knowledge I have acquired so far. Basically, I'm a field worker, like there are a lot of experts are here to talk more and give someone lectures. But for me, to talk something, rarely I will take some lectures for BTech students and for PhDs. Okay. So if you see my qualification, you can understand. So more like industry experience rather than research. But they put me as a scientist, and they're also still I'm roaming everywhere. I length and breadth of this country. I visited so many oil fields, and I also have students from various background. They are from mechanical, chemical, metallurgy, physics, chemistry. It's a kind of mixture of everything. Corrosion. So I started my career as a metallurgist. Then moved as a mechanical engineer, then somehow structural mechanics. Sir has given very nice lecture before me. So while I was going through this, I saw that he has covered almost like half of my presentation. So he made my job easier. So without making more time loss, I'm just going to my presentation. So he has given already a lot of introduction. So basically, I'm a diploma holder. I started as a diploma in mechanical engineering, and I went for metallurgy. Then again, additive manufacturing based MS research in IIT Kharagpur. Then I wanted my PhD in mechanical engineering. So now I'm working with corrosion. So you can understand, various fields I'm working. Basically, my major working area was in oil and gas industries. Okay, I worked for Technip ASA in Oslo. So I was working in let's say minus 40 degrees Celsius many times. Okay. So if you look at that percentage, I think that admit part, can you just close it? So corrosion is like almost 4% of GDP of our country. So if you see, our World Bank is projecting India might develop in the range of 6 to 7% this year. Let us imagine we have no corrosion in India, then it's going to be 11% GDP. Can you believe it? So most of the times we will skip this issue. Then it will become a very big issue. That time we will be called. So that is what happening in this country most of the times. Okay, unfortunately, rather than we will apply all kind of corrosion prevention techniques, but still there is a room for failure. Okay, so we will see one by one here. So corrosion is basically like when you give corrosion protection. I always remember my first HOD told me, if you are unable to give proper corrosion prevention, then don't give any corrosion prevention at all. So that will make things easier for the structure. So I agree with that. And somehow, the one more proverb, which I'll follow. When my supervisor, the Norwegian guy, told me that, what do you think about your PhD? And I told, sir, I'm learning to do research. And he told, no, you are just correcting how not to do research. So that is what I'm following here. Okay. So most of the time, failure analysis. So we'll go through this and we'll find out that this problem should not be repeated again. Okay. So how the corrosion in seawater can be controlled? So for any application, engineering application, particularly the seawater kind of corrosive atmosphere, you must take care the best material. So that is the first level of defense for your corrosion. Okay, material selection is a paramount for any application, I will say, not only for corrosive application. Then whatever you are doing, that is kind of supportive. So if you choose the wrong material, you can give anything, any kind of production, something will happen in future. Okay. Of course, we have some corrosion prevention methods like sacrificial anodes, coatings, and various other forms of corrosion techniques. Yeah. Sir also touched upon this. So he talked about tectonic failure. So there were so many issues during the World War II. I think this happened before that. But during World War, the people were getting a lot of ships were like broken into two pieces. And they were wondering what is really happening there. Anybody say what is that terminology? Just like 2 lines. It's called tactile to brittle transition. Structural engineers knows better than us. So material will be tactile at room temperature. But the moment, you are putting it into water, which is very low in temperature, it will become brittle. So as a industrial guy, I will say that we will do a lot of impact testing to check its brittleness, particularly the pipelines which are going into subsea. And do you know the water temperature in Western countries? It will not be like -20 or like that. It will be 4 degrees Celsius. So we will check the material up to -50 degrees Celsius to make sure that it's still withstanding its ductility so that we will not see such problems. So mainly like the materials background will also give us like more advantage. So if you go for very low temperature, we will increase the percentage of nickel, okay? And side by side, you simultaneously have to play around with chromium and some part for molybdenum, okay? So you have to take care of everything and then you have to choose the right material. So otherwise, you will see such failures. So, maybe I think you can help me. Okay? Yeah. This one is also important in India. So I worked a lot with Western oil suppliers. Mostly like they will prefer like 12.5 meter length pipelines. I will say that the pipeline industry is highly standardized one. I will say, next to none, I would say. So even our India, when they want to do something related to windmills in offshore, and they will go based on pipeline industrial standards because they are developing now for offshore standards. But basically, our country has requested help from DNV. So that stands for the Norska Veritas. So Norwegian verifying company, okay? So that is the only kind of sole technical supply provider for offshore industries in India. So India is planning to make a huge offshore investment in Gulf of Cambay and near Rameshwaram, Bombay area, where we have our own SICRI-based Marine Corrosion Evaluation Center. So I frequently visit there, at least like once in a month, we will go there. And my student is also there. So that's such a very good place. The second highest corrosion causing place in the world. The first one is near Red Sea, okay? So there will be a lot of conflict, so you cannot do a lot of analysis there. So the only place, a lot of countries, not only India, Russia, Belarus, USA, and they are testing their components for more than 25 years. Still they are doing. And we are doing a lot of work for our defense industries, So I'll touch upon a few projects in my last segment of presentation. So you can see that. So coming back to this line pipe materials, this 12.2 meter length is the kind of standard as per the DNV OSF 101. We call it as a Bible for subsea oil and pipe industries. That's standard. So I will say that is a very stringent standard in the world compared to ASTM, ASME, and several other standards are there. But I found this DNV OSF 101 is very stringent. And the pipeline can be classified into various forms. You have the general forms of carbon manganese steel pipes. We call it as seamless, submerged arc weld longitudinally, submerged arc weld helical. So that's abbreviation, okay. And you also have something called clad or lined pipe. If you see that the bottom three pictures, the middle one is a clad or lined pipe, okay. You can see the color change. So you will have a carbon manganese steel pipe. Inside you will have a very thin piece of like 316L, like Inconel, something like that, the material which can withstand more corrosion. And we also have the entirely corrosion resistant alloy based pipe materials. Just next. These are the types of stainless steel. I am not going very deep into metallurgy because during my college hours itself, we requested our professors don't have any lectures after lunch. So I'm not going very deep into metallurgy things. So you see here, there are several types of stainless steels. And if you look at the stainless steel itself, so a scientist developed steels. They call it a stainless steels because they believe that it will not give corrosion. And recently they messed up a lot when you do welding and other things. They will get so many problems in stainless steels alone. The carbon manganese steel is easy to weld, but the moment you go for stainless steel, you will end up with all kind of problems. So you develop some new systems and you will get more problems. So most of the times when I get the stainless steel issues, I have to start from the scratch, start from the material, do several analysis. If it is carbon manganese steel, we can easily find, oh, this is a problem. Okay, we can solve it. So with development, also, it brings a lot of challenges. Yeah, I'll try now. So the first set of inspection. So these are the pictures taken by me. Let us say something around minus 20 degrees Celsius in somewhere near North Pole. Okay, so we were making our own pipeline installation. That project went for like 3.5 years. So frequently I used to visit there and we go to make something. Can you believe that? How long that weld might have been carried out? How long ago that weld might have been carried out? It was done one day before. Okay. The next day we saw that issue. So that's why I said, if you have stainless steel, you will always have some issues. Okay. So such a fast way of getting problems. And 2 months before, we received a kind of a group of people from railways, and they are putting new, railroad, let's say like railway tracks, not road, okay, railway tracks in Bomban area. And they are using a combination of stainless steel welds. And they told the same issue. Sir, we completed the weld one day before. The next day, all the welds look like chocolate color, sir. Then I told, yeah, there might be some issue with your welding procedure, correct it. Because the one course which I went for after my PhD was welding, okay. I went for that's the rigorous course I ever attended, even bigger than my PhD. So they asked me to do all the welding by myself. So they will ask me to qualify everything, okay. So that because of that experience, when we deal with weld, I'll say that is the weakest link in any structure. So we will not give much importance to weld. That is the problem. Now, when I talk about corrosion for pipelines, you can simultaneously apply that same issue for shipbuilding also. Because the only difference is we are talking about subsea pipelines. The ship is just touching the water. No? It's not going into the water. And we also have something called submarines, which is like it's like almost like subsea pipelines. So we have the similar kind of issues. So recently I got a project from our Indian Navy. So we are working with that in Mandapam, that project we are going to start it. So I'll present particularly this weld. And you see here, this is the Norwegian Augusta Vekstadera. They are talking, so eager full work happened with the welder. That is what it's stating. So the cost of the weld is approximately in Indian rupees, if you estimate something like around 2,000 rupees. Okay. So what they did, they chose the wrong material. Actually, the pipeline is 6 moly steel. So when you say 6 moly steel, whenever I want something for subsea or the pipeline which is touching water, seawater, I will always prefer 6 moly steel. So this is always very good, first choice of material. But when I go for welding, so what they did, they used 316L stainless steel, which is having 2.5% molybdenum. And it failed exactly in 3 locations. You can find out 1, 2, 3. And the cost of failure was in billions. Can you believe it? So the prime ministers were even talking about it. Scottish Parliament was saying that, so we will sue that country, because you spoiled our seawater. So almost like 2,000 rupees weld started a kind of trade war between countries. So you can understand the importance of welding now. And whenever you used to work with stainless steel, because I'm concentrating more stainless steel, welding and corrosion, they are kind of interconnected because we are going towards more stainless steels already started. So you should be very careful whenever you work with stainless steel, even a small error. You use some wrong brush to polish it. I told now within 1 day. So we did it in the afternoon. So when you come back after like, we will go for like a 24-hour cycle. If you come out till 9 o'clock in the night, it will be corroded. So the corrosion will be very quick. Whenever you have stainless steel, you should not bring a high carbon steel, not near to that, okay? You just keep it for a long distance. Same one. So they used a wire brush and they started corrosion within a day. So these are the kind of effect of stainless steel. You invent some new stainless steel and it will create more problems when you go for welding. It's a kind of example, like the people were working with stainless steel and they were doing some kind of grinding work. And it started this kind of, we call it spatter. The spatter is kind of, highly enriched chromium layers. And when seawater or normal water, even when they are touching it out, they will just wash it out. So it will take a minimum like 3-4 months, not more than that. So you see here, there are a lot of issues. And if you leave it like this for, let's say, like 6 months, you will get corrosion problem. I'm not going into this because, I'm talking so many cases also that might be boring. So naturally, when you have stainless steel or the steels with kind of more advanced steels, you want some passive layer, which is Cr2O3. That passive layer should not be removed at any cost. So when it gets removed, you will get the corrosion issue. And when you have a welding, actually, it's for your ship also. So it's already welded. You should not bring one more weld near to that. So that will like make your microstructure more refined. Then it will expose to higher level of corrosion. So it's a simple methods. And these are the errors we found out, in our workshop, when somebody is doing weld overnight and the morning we found out that they have a welding and one more weld is stopping nearby. So that is not acceptable. We have several ways of understanding the corrosion in seawater. But, whenever we designed any subsea pipeline system, we design it for like minimum 25 years, okay, lifetime. So once you put it in water, so it's very difficult to go and do the analysis, normally. The maximum water depth, which I worked was like 1,000 meters. I think it's more than that in Brazil, okay. So imagine it's almost 1 kilometer depth. So you will not see the sunlight and it's very difficult to analyze. You don't know what is happening there, downstreams. So once you put it inside, you have to forget it. So You must be very careful what you are doing that. And some of these water pipelines, you can see that the corrosion, even we gave these anodes, they were eaten up within like 1 or 2 years. The wrong design of anodes, So such problems we severally face, and we will retrieve and do the analysis, and then we will do the repair works. And so the new methods, we are using now with subsea pipeline analysis, like laser mapping, because you cannot go into deep water. So we will use such kind of advanced technologies like remotely operated vehicles. So India is also kind of concentrating more with this one. I think there is one company in Cochin. They approached us like we want to do something similar for underwater structure like this ROV, and we want to design a new kind of equipment so that we can find out what is happening inside water. And we also have this unmanned aerial vehicles. So I'm not going very deep. Small things. I'm going to give some pictures, not many. And this is one of the super duplex stainless steel. It's not magnetic, but at the moment, you saw a big hole there. It was leaking out. And when I just to bring a magnet near to that, it became magnetic. It should not be magnetic, but it became magnetic. So we found out that the problem is we have to heat it something like this. But what they did, they put it like this. So that means like the wrong heat treatment made a component have highly segregated layer of chromium carbide, which is kind of washed out. And around the hole, we found out like more amount of chromium carbide, which is magnetic. I'll go very fast, okay? I'm not going to like. So similarly, like when you make a weld, we should be very careful. Like we will look at the top side and we will say that the weld looks very good. But when you see that inner side, the weld is not at all good. So the inside layer should be thorough and clean whenever you're doing welding for any pipeline section. And titanium material. So whenever I get titanium material, it clearly states you just see that color of the titanium weld. If it is like silvery colored, the weld is good. I'm still scratching my head how this standard has arrived for such conclusion. You have some colors and suddenly you are saying weld is good. These are, I skip it because it's something related to structural engineering. So I'm not going very deep into that. So this is the pipeline section. We just roll it, and if you see the diameter of the pipe is something around 350 mm. So you can understand how big it is. So there is a guy standing here. So it's almost like 75% of his height. So we'll reel it and re-reel and then put into the water. So similarly, we are applying a lot of the paint systems and other things to protect the pipeline, which is going into the water. It's not only pipeline system, the entire oil rigs and various structures, whichever is going into water, we will give various protective measures. So I'll always close up my presentation with this slide. Sometimes we scientists or engineers can do something over. So we will end up something like this. So we will get a very good weld and we spoiled all the pipelines, okay? So the welding is like that. It involves several engineering backgrounds, metallurgy, chemistry, physics, structural engineers, so many things, When you want to do something very serious, you must always wait for some surprise. So this is one of the worlds, I always like. The world was an excellent world, let's say best in the world, but it spoiled the entire pipes due to previous corrosion. These are some classical projects. These projects, we did it for our fishermen from Chennai, and they will have their rotor plate for their fiber boat. And every 2 days, they have to change it. And they came up with some issues for us and say that some of our fishermen were sitting in Bay of Bengal for like 4 or 5 days. When it is broken, they don't know how to come back. And they approached us, and then we created a kind of new coating system for them. So at least our new coating system told them that they can change that. We cannot completely avoid it, but it was going for a month almost. So at least they can have 1 or 2 with them, and then they can be safe on the sea. So it's a kind of communal work. Sometimes SICRI will ask us to carry out. And this is our testing yard in near Rameshwaram. Whenever you cross the Bomban area, you can find out our SICRI is having. We have a kind of special Stevenson chamber. We mimic like it's a simulation of a house situated near seashore. It may be something around 50, 60 meters, not far away from the sea. So we'll put all the samples in there and then we'll monitor it for years, okay, sometimes like 20 years. And most of these times we will go for like 6 months or 7 months, and then we'll find out so what's really happening. And this project we are currently running for Saint Gobain, and they are evaluating their defense-related mirrors. Can you believe it? How mirrors are behaving in seashore area? So such interesting projects will come, you know. And this is a project I got from Indian Navy. So they want to know, so what is happening for the material when you put near the seashore and inside the water. So we are going to immerse these materials for Indian Navy and monitor for like almost 3 years continuously. And wherever we have the defense related, our SICRI's contribution will be there. As you see here is our rocket is going to be launched by ISRO, and SICRI has provided the paint system because they want to store it for a long time in Sriharikota, the near seashore. So they don't want to spoil it before they launch. That's the last slide I'm going to complete, sir. And we have several project possibilities. A lot of students were not aware of that. So if you want to come for your thesis work, it's highly competitive. You know, this year like we received more than like 250 applications. So I think only like 20 or 25 got it. But still we have, you know, so every year like 2 kind of application you can start on 15th of March and 15th of November. So we got it, and the selection list has already been announced for this year. So we have several kind of requirement here. You go through this in our website, and if you want to apply for it, you can come for it. For MTech, I think it's you have to stay for at least 125 days. That's a mandatory requirement. And I also got several students from NITs and one student from IIT. So they worked a lot with metallurgy and welding, corrosion related areas. Most welcome. Done, sir.
Okay, thank you, Dr. Ganesh. It's very interesting work.
Thank you, sir.
A lot mostly to marine area, I find that.
Yes.
Subsea pipelines and including propellers effect.
Thank you.
It's a nice thing. Any question from the audience?
I have a comment and a question. Nice talk.
Thank you, sir.
When you went to 1,000 meters, knowing the chances of failure, I think it took a lot of courage to go to 1,000 meters. Water depth.
No, actually, we will not go deep into the water. Actually, we will be standing over the ship and then we will be doing that one.
That's different.
We'll say that. The maximum depth which I went was something like 150 meter. Once I went with the habitat, okay. That was challenging work, and they put me in water for like 1 month. You know, normally they will follow safety standards. So I'm kind of certified for working in sea water and then over the height. So when you go for offshore, you have to pass all this tests. So 150 meter was the depth I went, not more than that. Yeah.
I've been in an old submarine many times at 50 meters depth, which was okay. Question is regarding the propeller.
Yeah.
What caused the failure so quickly?
The thing is like the project, what I showed you.
Yeah, the fisherman's
The
propeller.
fisherman's one.
Yeah.
It's a kind of a combined effect of erosion and the material what they were using it. They are saying that the propeller cost is 250 rupees.
Okay.
So you can understand it's a cost material. It's not forged one. So we cannot blame them, because they want something like very cheap.
Mm.
And they cannot change the material. They told frankly, sir, don't give something like to super duplex stainless steel. We cannot buy it for 1,000 rupees. The fisherman will not buy it. So you have to give some coating. Maybe like if it is 250 rupees, after your coating, it can go up to 300 rupees. That restriction also they gave. So maximum 300 rupees, you can go, not more than that. So I went up to 280 rupees. So like 30 rupees more, and they can use it for almost like 1 month. So this one we did it for societal things. So yeah.
Dr. Ganesan, I have one query. Earlier, Sikri Karakudi used to do some consultancy for Cochin Shipyard regarding cathode protection.
Yes, sir.
Still it is going on or stop?
Actually, our cathodic protection team is doing enormous work. Recently, they did survey for our Cochin shipyard.
Oh, I see.
And I think India is building our aircraft carrier here, isn't it? So a lot of several defense things, so I cannot reveal it here. So we are constantly coming here. For Cochin, we are coming here, and almost all the pipelines in India we are visiting. And our team is getting kind of more work order now from various industries, particularly in that cathodic protection area. Some of the people are getting the old methods now. They want it. Yeah.
Any questions?
Sir,
Hello.
I'm Shafina. I'm a research scholar of this department. I'm currently working on microbially induced corrosion in subsea pipelines. Sir, can you suggest any
The MIC thing is like, we have a separate group for it. And normally we will work together. We recently got a project for GAIL, Gas Authority of India Limited. And they told one of their main issue is MIC. So when you leave a pipe for like around 1 month to 6 months, sometimes they will not do any activity there. The water or something liquid, which is like stagnant on the 6 o'clock position, we call it. And that area with the microbes, you have several microbes like the oxide reducing bacteria, manganese eating bacteria, so many things, Those bacteria will be kind of main cause for this issue. So normally we will recommend biocides, as you know that. And we also have a lot of restrictions for biocides. You cannot simply add them. Yeah. Yeah. The thing is like first preference will be cost. That's really important. The second one will be the environment. So if you see kind of both of them are kind of satisfied, you can go with any kind of biocides. But recently, what I recommended for Gujarat Alkalis and Chemicals Limited, they have some issue with the same microbial corrosion. We recommended neem oil and aloe vera gel. Can you believe it? So go for the green biocides. So that's what the industry is also expecting now. And as far as my understanding goes, if you can use, I think 2 or 3 biocides made of green materials, most of the time it will work. But the thing is like you have to check them, You have to literally apply and check it. And in case of this Gujarat and Alkalis company, they told me to check it for 6 months. So I immersed it in aloe vera gel. And you see that, it's a different kind of corrosion work. And we found out the microbial corrosion is coming down drastically. Yeah. I will recommend go for mixing any greener biocides. Yep. Thank you, sir.
Thank you, sir, for the enlightening talk. I would now like to invite our session chair, Professor Dr. P. Krishnagutty, to present a token of appreciation and a certificate to Dr. S. M. Ganesan. Sir, please.
We'll have the next presenter, Dr. Santosh Kumar, who is going to talk on artificial intelligence applications in maritime industry. He is a professor in the Department of Computer Science and QSAT. He received his MTech and PhD from this university. He also worked in Malaysia. And he is a visiting researcher in Queen's University, Belfast. He co-authored 2 books and is the senior member in IEEE. And he specializes in formal modeling, cyber physical systems, natural language processing, etc. Thank you, and call upon Dr. Santosh Kumar to give his presentation. Thank you, sir.
Okay, good afternoon. So I thank the organizers for including my name, even though I am far from ship or ship technology related stuff. But every industry or everything is approaching us for doing a lot of things. So we do a lot of machine learning and AI. So I have one question first, maybe a couple of questions. So I will start with that. Do you know who won the Nobel Prize or for which contribution this year's Nobel Prize was given to physics? Physics Nobel Prize 2024 was given to for what technology? Okay, so it was given to 2 people, John Hopkins, for developing artificial neural networks. Do you know for which technology the chemistry Nobel Prize was given? Nobel Prize in Chemistry 2024. For which technology? It was given to protein folding problem and uncovering the crux of protein folding. And it was given to 2 persons who are working in a company called DeepMind, which is a Google company. And the problem was solved by AI. I mean, machine learning or deep learning stuff. So I will start with where Nandakumar sir just, stopped. So he was just detailing on finite element method from 70s to 2020. So I will start from there, 2022, maybe present. What is happening in the industry, basically. Maybe I won't go into the deep of machine learning or artificial intelligence related stuff, which maybe I'm very much confident. But I'm just trying to look at what is happening in maritime industry based on AI and machine learning. So this is maybe a kind of a broad overview of what is happening. In between, I'll be touching upon some aspects of machine learning and AI and maybe some problems that can be solved using machine learning and AI in the marine industry. Especially in the shipping related things. So this is the agenda. So I just wanted to brush up what is AI. Basically, Nandakumar sir has given a very philosophical kind of an introduction. There is, I cannot, reach up to that level, but just for the sake of understanding what I'm telling, basically I just show you some figures and tell you
what is basically behind the AI. And then why industry is actually adopting, or what is the adoption, why industries are adopting AI to solve their problems. And then a lot of application areas for automation using machine learning and AI, and the challenges. So this is the brief agenda. So just I want to unpick AI concepts. So maybe as you can see where the artificial intelligence kind of stuff stands, and what is basically machine learning, and what is basically robotics. And I have given 3 examples which details what is basically artificial intelligence. So making machines intelligent is the basic task of AI. And IBM has come up with a Deep Blue kind of chess playing game, which is regarded as artificial intelligence. And this part you can see ATM. I mean, if you are given a check, for example, written and signed check, and ATM can read that check and understand the person who is submitting the check, and it can deny or pass the check. And this is called basically machine learning and making machines that learn. And robotics here, juncture, basically it has some component of machine learning as well as AI. So maybe as a textbook style kind of a presentation, if you ask what is learning, so there are kind of learnings called, we call it as supervised, unsupervised, and reinforcement learning. So again, we can classify this as supervised, unsupervised, semi-supervised, and reinforcement learning. So you can see what kind of I mean, data is being actually used while doing this problem, and what kind of problems they actually solve. So usually they do kind of a regression or classification, clustering, then association kind of a problem, then control kind of a problem. So these type of problems are basically addressed by maybe broad category of learning algorithms. So if you ask what is supervised learning, basically you have some bunch of data with labels, right? You have a picture of cat, and you say that this is a cat, right? So that is what we call as a label, right? And what you do is you do a kind of a model training. That means you are giving the bunch of data to the machine so that machine builds something, right? So we call it as a model. And then we give some test input data, which might be from here. So you say this process called prediction. So whether it predicts it correctly or not, based on that, maybe we train that. And we train this model in such a way that even if it sees an unseen data, it should be able to predict that. So that's the main goal, or what we call prediction, right? So in unsupervised learning, basically we don't have labels. We have just data, right? We have just a lot of pictures are given, and we haven't labeled it. So this is an unlabeled kind of data. And then you do the same thing, and you try to recognize some pattern from that. And semi-supervised learning basically has little labeled data and a lot of unlabeled data. So all these are realistic things. That means we may not have much data with us. So how to solve that problem? So usually you have a little bit of data. For example, in medical science data, you will have a small set of data, but you will have a much unlabeled data, and you do the same thing, model prediction. Then maybe you have the model, and you can use the model to predict the unseen data. And reinforcement learning, basically it works like this: agent and environment. So you are doing something on using an agent, and it produces some action, and then this environment gives you some reward. So agent will get some reward, or maybe some kind of punishment, or some kind of a reward agent will get, and based on that it learns. Basically it is something like maybe how humans actually learn, right? And if you look at the programming style, so this is the conventional kind of a programming style where we have explicit rules in order to do something. So for example, here we have a program for identifying what is fake or junk kind of a, or spam kind of an email. So you have if then else conditions, right? So this is the conventional way of writing explicit rules. But here in machine learning, basically what you are doing is you are giving a computer program to learn from the examples, right? So from examples, it learns and builds a model. So that is the difference between the conventional kind of programming and the programming for the AI or machine learning. And if you ask me what are the things can be done using AI, so we are here, actually, we call this as a narrow artificial intelligence. That means we cannot do much. I mean, we haven't attained that much level, and maybe we are able to perform only one specific task, right? Human beings are not like that. Human beings are versatile. I mean, having a versatile brain, they can do a lot of things, right? But in machine learning, when you say narrow AI, you have one model doing one thing, right? For example, while you're capturing a photograph through your smartphone, it detects the face of people. So it can do only that thing, right? Nothing more, nothing less. But we are targeting towards general artificial intelligence, maybe 100 years down the line, we might be able to do various tasks using the same kind of program. And deep learning has made a lot of advancements in this learning kind of a task, where deep learning is basically you have a bunch of layers of neural networks. It learns a lot of maybe, as Nandakumar sir was telling, its only function is to learn a function, which is, we don't know, actually a nonlinear curve or something like that. So neural networks are very good at learning functions, right? So such a huge number of neurons packed as a layers, right? And that's why it's called a deep learning. That means you have a lot of layers, and layers are actually trying to learn some patterns from the data, and maybe the learned pattern is actually back propagated to look at what kind of errors are there, and then again it goes forward and reduces the error, and finally it tries to do its task. Basically, it's an optimization problem. You are trying to optimize things. So there are things which is driving the entire AI era. One is big data. That means you have huge amount of data that is available, right? So this called, we call it as a big data. Then another thing is rise of GPU computing, right? Computing power that is available to us is huge nowadays. So especially based on the graphical processing unit computing. We are aware of CPU based computing, but now we have big chips where we can do a lot of processing using graphical processing units. And there are a lot of sensors that is available. So from where this big data is coming, big data is generated by people, big data is generated by machines, big data is generated by through the environment. Everything is captured by a lot of kind of sensors. And these three things actually enables the era of AI. And maybe these are the names you might be familiar with: ChatGPT, Copilot, and Gemini. They do wonderful things by generation of text, basically. So you might be wondering how these software are actually able to produce some text, right? So while you are typing your email, hello, then how are you will be automatically filled by the, right? So it is coming from, it learned a lot of kind of such texts, right? And it knows from after how or then it knows you, right? So automatically it fills that, right? So, and again, images, right? It generates a lot of images, right? If you go to Gemini and ask just give a situation, it will generate a very good image, right? So this is also due to the training data that is available and computation power that is available to the. So now let us see a ship maybe. So how we can leverage this big data and what kind of sensors or what kind of data that is being available from the ship. So because every machine learning or AI related thing starts with data. So if you do not have data, then there is no need to maybe touch your hand on that problem, because without data you cannot do anything. But here maybe since this industry is using a lot of sensors, a lot of data that is available for you. So some of the sensors I just noticed and I just listed it. So one block of sensors are called navigation sensors. You have GPS, gyroscope, accelerometer, magnetometer, radar. Environmental sensors are there: temperature, humidity, barometric, wind speed, water quality sensors. Then engine and machinery sensors are there: engine speed and load sensors, fuel, oil pressure, vibration sensors, right? Then structural health monitoring sensors, strain gauges, accelerometers, etc. So a lot of sensors are, by the way, this is a generated picture from Gemini, right? So maybe it looks like a realistic ship. Okay. So yeah. And another stuff is you can connect, right? Connect through the communication equipment like, I mean, mobile towers, right? Radars, etc. You can connect and maybe send and receive data. So that is another advantage. So I have just gone through a research report where it says that exactly the same sentence: growing maritime industry with AI. A lot of ship builders or ship owners or the ship industry people are now interested in AI. So let us see what kind of problems actually they are looking at, right? So what they have done is they have captured 125 companies, right, which are involved in AI technologies. And this is a report published in 2024. So last 12 months, and 36 companies that have announced their purchase or plans to deploy AI-enabled technologies. So you can see the SMEs are more, right? Small, medium enterprise kind of and you see corporate companies also very much interested in investing or buying some technologies related to AI, right? Then why they are interested? So why they wanted to adopt AI related things, right? So we have one demand, which maybe your solution or your entire industry must be energy efficient and it must be safe in terms of operations. So these are the two driving forces for the marine industry to adopt AI. So you can see that. Can I? Yes. So you see this, the cruise shape is producing this much of greenhouse gases, right? This is the most, I mean, top in the list, right? Okay. So you have United Nations Sustainable Development Goals, right? And the goal 13 says that climate action, right? So the marine sector, whose greenhouse emissions have risen to 20% over the last decade, right? So we have a responsibility to optimize maybe the release of gas, or maybe you wanted to do efficiently, maybe sail your ship, or so a kind of optimization is actually required to attain this goal, right? Okay. So some examples, maybe a company from Norway. So they have secured 44 million Norwegian krone for Propel sustainable shipping. So everybody is talking about sustainability, right? Shipping industry is not far from that, right? Sustainable shipping. Then again, Orca is a Israeli company. They also secured a US dollar 23 million in this May, following collaboration with North Standard to further their enhance its AI platform. So I'm just giving some of the examples where industries are actually interested in doing things. Only they wanted to, save on CO2 emissions. You know this company? Anybody? Elon Musk company. So Elon Musk has offered through satellite internet connectivity, high speed internet connectivity through satellites. Now all the boats, ships, everything will be connected each other, right? Through this links, right? Okay, this was for my reference. I was just so I just wanted to give some of the problems which AI can, people are trying to solve. So one is OH optimization. Another is condition-based maintenance, autonomous navigation, safety and compliance, energy management, port management, and ship design. So in these areas, you can find a lot of problems that can be solved using, machine learning or AI related things. Basically, you do optimization. So I will give you some of the examples. So in voyage optimization. So this is another company, Deep Sea Technologies. It partners with shipping and driving AI adoption, equipping tanker fleet with deep learning based voyage optimization tools. So we have automatic identification system data. AIS, almost all the marine companies have contributions to this. Are you aware of this AIS data? Automated identification system. That means whenever you sail a boat or ship, you are generating a lot of data. Maybe where this ship is now, right? How much nautical miles from the shore, right? All this data is being logged. All this data is available on a server, right? So and this data is being actually shared with people who can develop a lot of applications based on this. So what kind of data is available? So maritime mobile service identity number, then IMO number, call sign, ship name, length and beam, type of ship. So these are static information. The navigational information, course over ground, speed over ground, heading, navigational status, rate of turn, voyage specific information. So what is a ship's broad, hazardous cargo or not, destination and ETA, route plan, right? So while a ship is sailing, you have this data and it's a continuous data. You can contact the server and find this data and you can locate, right, where the ship is now. Based on that, you can plan a lot of things. For example, in the port, right, people must be ready to receive that cargo, right? So they can plan, right? So or is there any delay with the ship receiving, coming to the port, right? They can permit another ship, right? Because they wanted to reduce the delay at the port, right? The demurrages charges, right? So that is very crucial, right? A lot of things. I was just giving an example. So Pythia is a software. So it's an AI powered voyage planning kind of a software, right? Which is already there in the market. So it gives the routing, right? How the route can be optimized. In terms of energy or in terms of time, you can optimize the route of the ship. And the algorithms are actually trained on the real-time data. So there are a lot of other software, Cassandra, Hyperpilot, Neuro. Those softwares are doing, AI-based kind of thing. So this is endorsed by Class NK platform, right? So any software that must be released must be endorsed by Class NK for the professional use. Another companies which Eastern Pacific Shipping, they roll out deep sea technologies for platform fleet wide. Then K-Line, which is a Japanese company, they automates lay time statements with AI powered OCR. So this is a very interesting kind of a stuff which is powered by ChatGPT. Backend ChatGPT is actually reading the OCR document, documents that is produced, and they calculate what is the lay time, right? How much time the ship was actually anchored on a port, right? So those aspects it's automatically reading and taking decisions. Then HD and Hyundai, right, delivers bulker designed to operate without an engineer. It's an automated kind of a ship which is actually tried, and it is released actually. Then some work on data-driven condition-based management. So you have to predict, right? You take the data from the onboard sensors and predict equipment failures before they occur, right? So this is maybe you can schedule in such a way that maybe before failure comes, you maintain. You start the maintenance of the ship. Otherwise, maybe you may have to wait till the ship is giving some complaint, right? So data-driven condition-based maintenance maybe help you. So you have onboard data, a lot of data is there, and from that you have to understand what is basically happening, and is there anything to be done to the ship, right? Before it gets failure, right? Then autonomous navigation. So same thing. Basically, small boats, maybe without a person who is driving the boat, you can use AI algorithms to as you have seen automated cars, right? Then safety and compliance. Basically, there are a lot of safety rules to be followed, right? And usually what happens is a seafarer may wish to find out how often and how they should calibrate the gas analysis. I'm just giving a scenario. So instead of searching through the documents and trying to find out the answer, the user can simply ask the assistant. That means AI assistant. The tool will provide the answer and the source of information. He may have to have a reference, a solid reference before taking a decision. And the tool can maybe search on the huge amount of data, and it can give the suggestion as well as from what information or from which book, which manual this the solution is coming. So all these things can be automated very easily. Then port management also, as I was just pointing out, you can optimize the process that is happening at the port. And ship design. Recently, I visited Belfast, and I have seen this. This is converted as a hotel. This is where the Titanic ship was actually designed, right? So this is now a hotel, which they call it as Titanic Hotel. And so how the ship was actually designed. So a lot of engineers maybe standing, they are making a lot of drawings and all, right? And then they have to design the ship, right? And then maybe there is a process, maybe this is an old process they have to follow, Evans spiral, and then they have to test it, right? So this is with towing tank, and they test that with the different conditions and all, right? Before building the ship and releasing in the sea. So nowadays, people use CFD simulations, especially you might be knowing this star CCM plus kind of Siemens tool, which will be, giving you computational fluid dynamics based simulations. So basically what I understood was you have a structure which is touching the water and you wanted to, to model how optimistically it can, optimize the way of plotting the ship, right? You wanted to reduce the frictions, right? A lot of things you can do using this CFD simulations, and you can start with a CAD kind of a diagram, right? And meshing you can do. Then you can have a template based setup, and you can analyze the designed design, and you can make modifications on that, and maybe you can finalize this. So this is basically based on the CFD simulations. But industry is coming up with a lot of algorithms which drives this. Even people are believing on towing based stuff, right? So these are some of the examples where which has done in this CFD simulation. So here a ship basically tries to float through icy kind of a sea, right? So how the ship is getting friction based on this environment. So this can be simulated and studied. Also, the simulation based on the turbulent flow and the hull. So what is the friction over this hull, that can be also simulated and see. So so hull optimization, basically you have the hydrodynamics performance based based on the existing hull forms, right? So there are a lot of hulls already been designed, and based on that you are studying the hydrodynamics, and you can do the regression approach, and you can see what is the advantage of giving regression. Basically you can study the parameters which are actually lot of parameters which are connected, and the connection will be not just linear, it might be non-linear. So non-linear hull surfaces you can study, and then you wanted to improve the performance, and you have the engineer there. He has a personal experience to revise the hull plan, right? And but maybe it depends on the designer's skill, and it's he finds it very hard to find the optimal configuration. So a person with a lot of experience can be replaced with artificial intelligence with a lot of hull forms which is given as an input to the AI model, and it learns a lot of things, and it can suggest a suitable hull form. So that is what basically we are AI people are doing. So one of the example is something like this. This is a published paper. So predicting the total resistance of ship hulls based on geometry modification parameters. So that means you have a lot of data with you based on the geometry, and you you train the model in such a way that it checks with the modified parameters, like it changes length, width, height, right, draft, and hull surface. A lot of things it changes, and finally optimizes the design and gives it to you. And it is found that the average error was lower than 4% when compared with the CFD data. That means the power of analysis by AI is huge. That means you have huge designs, huge number of designs. From that, it learns a lot of things and trying to optimize the given design. Yeah. So another example is, see, you have biofouling, right? Biofouling, you can easily do it with a picture that is captured from a camera, underwater camera, and you take that and you do an image analysis. So it will classify what kind of fouling is actually is there. And this work they have done, 7 classification, 7 kinds of biofouling, and they have correctly classified it. So there is ship weather routing system. Then the hydrodynamic performance prediction using neural networks. So this is again a very nice work. So using machine learning, you can do a lot of stuff. So fault diagnosis, ship design recommender system, ship movement classifier, time series data classifier, condition monitoring, and in the regression analysis, propulsion power prediction, biofouling level prediction, etc. And unsupervised learning, you can have anomaly detection, task allocation, power and fuel consumption estimation, etc. So basically what we are interested is we are trying to optimize things. That is the only thing with machine learning algorithms and AI we are doing. So there are a lot of applications, and which area that application is being applied and what kind of AI method is being adopted. I mean, I will leave the slide so that you can refer it later. One more stuff, as I told, there are a lot of data sets are available. So you start with the data. So I have just collected some links which gives you data. And these are the challenges basically. So as Nandakumar sir was also telling, that you must have a clean data, right? So data itself is noisy because you are collecting it from various sources, and you have to ensure that the data is mature. Otherwise, you will not get required results. But you have a lot of data, right? So that is the core principle of machine learning. If you have enough data, right? Enough data, you can do processing, and you can get better results. Then this is again data consent. Nowadays, when you install any app, it asks GDPR kind of thing, whether you are agreeing or not, right? So this is a problem, because most of the ship owners or ship builders will not share their data. So that's the problem. Then the trust and transparency. If maybe we are competitors, right? If I share my data, maybe whether it will affect my business, right? So that kind of a fear. Then regulation and ethical consent. So I will stop here with maybe by embracing AI, the maritime industry can unlock new opportunities, improve safety, and reduce costs, and contribute to a more sustainable future. So thank you.
Yeah, it has been a interesting talk about AI application is there in almost all area, mainly into marketing, and only thing is, as you said last, the reliable and data availability, and the owners of the data are not willing to share it. So less the data, less will be the predictions, and less reliable will be the predictions and all. Yeah, that's true. Any question? No, okay. I think thanks a lot. Thank you for that.
Yeah.
Thank you, sir, for your insightful talk. I now invite our session chair, Professor Dr. P. Krishnagutty, to present a memento and a certificate to Dr. Santosh Kumarji.
Okay, now we move on to the last presentation of the day by Dr. Ronnie Francis. So Dr. Ronnie Francis is a scientist G at NPOL. He did his BTech from this department. did his master's and PhD from IIT Madras Ocean Engineering Department. And he works in the area of flow-induced noise and computational fluid dynamics. He is currently holding the position of a project director of the ship, the Caustic Research Ship for DRDO. Yeah. So thank you. It's all over to you. Please go ahead with the presentation.
Thank you, sir. Good evening. I know it's a Friday. I know it's a Friday evening, so I'll make it as short as possible. And it's already, we have 1 hour behind schedule, I understand. So it will be very small. So before going to the topic, I am from this Naval Physical and Oceanographic Laboratory, which is in the neighborhood of this place. We are a DRDO laboratory. And out of the more than 50 plus laboratories in Kerala, this is the only laboratory of DRDO in Kerala. And we are mainly working in the area of development of underwater communication and sonar systems development, basically. So I am heading an ocean engineering division where our small division role will be to develop the hydrodynamics and structural designs, and then the handling systems for various sonar equipment like that, etc. But the lab mainly focus on the development of sonar systems, and so we need this in the sonar systems. You may be knowing it is all underwater. The only communication means is sound, because EM radiations or electromagnetic waves cannot travel beyond a few meters underwater. So like our mobile phone technology will not work underwater. So only long range possibility to communicate underwater is sound. As of now, there is no other means. And sound can go depending upon the water conditions. It can go up to 20, 30 or even 100 kilometers. That's what maximum we can get a range. And this is very important in the defense area, where particularly where we need to, when a submarine dives, it has got no eyes to see ahead other than its own sound which it generates. So that sound comes from the sonar system. So when submarine is completely dived, the only means of it to navigate forward and avoid collisions and communicate with the land or anything is through the sound. So this when we develop the sonar systems for this mainly for submarines for our Indian Navy, it needs dedicated platforms for doing the test, because it should not have so much of ambient radiant noise it generates. It should not generate a lot of noise, because the equipment which you are testing will not be able to see if there is a lot of ambient noise present there. So that is why this topic of underwater radiated noise becomes very important. And presently our lab is in the process of acquiring a acoustic research ship. So that ship is particularly, it's the first time in India an acoustic research ship is being developed, and I am the project director for that also. And this ship should have the minimum underwater radiated noise. So such a ship is never built in within the country. There are now some silent class requirements of DNV and all, where no rules are there. So, but first time in the country, we are going to build a acoustic research ship. That contract was signed with the GRSA Kolkata last month at our lab. So I'll just move on to the underwater radiated noise. Basically, this is my topic. I will say the sources of radiated noise, various types of radiated noise, like coming from propeller, machinery, and flow noise, and some of the methods how you can mitigate this radiated noise, and some cost on impact on design, class rules, what are the class rules and all, and finally, how to measure this radiated noise is what I'm going to briefly cover. So this is very important in the area of fisheries research. That's the most commercial application of this underwater radiated noise, where this noise has got a very detrimental effect on the marine life. Fish research particularly, if you want to study fish, the moment you go there to study the fish will escape by seeing the noise. It will affect their, too much noise also will affect their marine life also. So there, this is very important. And most of the regulations in practice today is coming from the fisheries research. The second one is the design on development of acoustic systems is what I meant for defense area. Since this is happening in a very shrouded environment, mostly secretive environment, there are no regulations and nobody knows what kind of noise these people are actually generating, people like us. So there are not much commercial regulations on that second part. Third one is environmental noise pollution, and again fourth one is the marine, the underwater noise from marine vessels. As of now, it's not regulated properly. There are not much rules and regulations existing which regulate this noise. So these are the major sources you can see coming from the machinery noise, propeller noise, and flow noise. And so this is the flow-induced noise. If you see the figure of flow-induced noise from appendages, there are a lot of flow taking place, rudder posts and all. Then propeller itself generate noise, and cavitation is another section of propeller noise, which is a major component. And machinery noise and from the flow noise coming from the hull. When the water simply flows over the hull, that also will generate some noise. So these are the major sources of flow underwater radiated noise, and it is strongly dependent upon vessel speed. And also at lower machinery, low speeds, this is mostly covered by the machinery noise. And at when the speed of the ship increases, it is dominated by the cavitation-induced noise. So this is how the split up basically comes. The internal noise, if you see, the cavitation-induced noise and machinery noise. The cavitation-induced noise is only happening when the propeller is cavitating. And that noise is broadband in nature. It has got almost many frequencies ranging from 10 hertz to more than, say, 20 kilohertz. That kind of range is there. And above cavitation speed, propulsor-induced noise will dominate actually. So, and I will come to some of the spectrum of the cavitation-induced noise. And machinery noise, you can see it is particularly relevant below 200 hertz because we have all these reciprocating machineries, and these engines and all are operating at their slow turning pace and all. So they will have frequencies to 200 hertz, and they will generate tonals. It's called tonal at a single frequency. And this is very, very important in the defense areas where we look for underwater radiated noise from particular class of submarines and all. So by looking at their frequency and pattern, it will be able to find. So this is what most of these navies will try to suppress when it comes to the machinery-induced noise. And this is the radiated noise. You can see the low frequency is generally dominated by tonal components. And the main, as I told, it's the main engine firing rates and propeller blade harmonics. And you can see the measured URN. It's that plot shows a underwater radiated noise measured on two ships. You can see one is a research ship and the other one is not a normal ship. So in the research ship, there has been a considerable effort to reduce the underwater radiated noise. And that is why that curves are apart. You can see there is a 20 to 30 dB difference in radiated noise levels. 3 dB means double. Because the dB occurs in the logarithmic scale. So 3 dB, one is 10 knots, the other is 13 knots, means it's only 3 dB, but it actually means it is double. So if you see 20 to 30 dB means it's a huge number beyond our imagination. So that kind of reduction is possible if you take a little care in the design of the ship and machinery selection with respect to underwater radiated noise. So coming to some of the specifics of propulsor-induced noise. One is cavitation noise, very, very well-known phenomena. We know that this is a section of the blade, propeller blade, and on the upper side we have the suction phase, lower side we have the pressure phase, and we know wherever there is a small area where this is a vapor pressure and it goes below. This is actually negative pressure, so it goes below the vapor pressure of water, cavitation occurs, and in that area is what we have generally the cavitation taking place. So cavitation and it can occur in the propeller tip as well as hub and hull appendages. You can see here two types of cavitation. One is the tip cavitation, that is what is happening, these lines happening, and there is also, it's masked here, there is a hub cavitation occur. So all these are the two cavitation examples. There are different types of cavitation like sheet cavitation, vortex cavitation, etc. And as I told, this cavitation generates bubbles of various sizes, innumerable sizes actually, small sizes to very large bubbles, and they burst at different frequencies. So that's why it results in broadband, very broadband kind of noise spectrum, where we have all sorts of frequencies are available. That's why it's written there. The noise is broadband. There are contributions from all frequencies. And this is a typical propeller cavitation spectrum. You can see there are, what you want to see, that spikes is 2, 3, 3, 4 spikes is the tonals, it's called. We are occurring at specific frequencies because we have the blade rate frequency. So, blade is rotating at a particular frequency. And if you multiply it with the number of blades, then that's what, and it's harmonics. And these are occurring at a single frequency. You will get, say, 200 hertz, you may get a 250 hertz. So that's what is occurring here as this tonals actually. And as I told, this is very, very important in the defense area, where they look for these tonals to identify what is that ship or what is that submarine coming. And this is the broadband part of the spectrum, which is over a 30 to 300 hertz frequency and all. And and the cavitation noise will increase, as we know, very well known. When the ship moves faster, the cavitation also increases faster, and there is a towing operation. Suppose a tug is towing another one, then propeller loading increases, and naturally the cavitation possibility also increases. So a lot of noise it generates. And ice breaking, and when you see dynamic positioning, some ships will have dynamic positioning system. There are also a lot of thrusters are there. So when these are also used, these to added noise and the noise induced spectrum. So reducing cavitation is the one of the most effective method to reduce noise is to reduce cavitation or operate in a regime where there is no cavitation. So this is why it is a reason for cavitation. It is also well known that one is the wake is highly non-uniform. You see the wake, this uniform wake curves actually plotted at the behind of a ship. And as you can see, it is a very highly non-uniform wake. And this is what deteriorates the cavitation performance of propellers. And another major source of noise in research ships, like what I'm going to acquire, is a research ship. There is a dynamic positioning system involved. So that involves a lot of this bow and stern thrusters, because you need to maintain the location. So these are more prone to noise because these are, first of all, it is these thrusters are located transverse, and they are where the hull lines are rapidly changing. So flow is highly non-uniform in that area, and there's a transverse tunnel thrusters are there. On one side of the thruster only you have the hub. So when it's generating port thrust, it is one kind of flow. When it's generating starboard thrust, it is another kind of flow. So, and this is a very highly non-uniform kind of flow taking place over the thrusters. So this bow and stern thrusters, or in a DP system, that generates a lot of noise actually. So that's what I have written here. And also shallow water, shallow water, there is a pressure is less. So it's again more prone to cavitation. So this DP or bow and stern thrusters will lead to a lot of cavitation and underwater radiated noise. And this is a mitigation of propeller noise. Operating the vessel below the cavitation speed is the best option. That's what everybody is trying to do. But, as naval architects, it is not that easy. Most of the time, as the speed increases, propeller will cavitate. And this already I'll change. Okay, correct. So modern propeller design method, there are propeller design methods available to maximize the speed at which cavitation occurs. So if you can simply shift the cavitation inception speed, that itself will lead to a lot of reduction in the underwater radiated noise. That's what is seen here. There are two propellers of comparable size, and both are operating at the same RPM. And in one case, the cavitation starts at 60 RPM. In the other case, the cavitation starts at 72 RPM. But the noise radiated will be much lesser for the propeller, which has got a higher cavitation inception speed. So another, the properly shaping the blades. That is Q. Submarine propellers, particularly if you have seen, you might have seen the heavily skewed propellers. Rather than have a simple flower-like approach, it will having a very highly skewed kind of propeller. Why advantages? It will have that blades as they rotate will more uniformly, that flow over the blades can be made much more uniform. if such Q is provided. So that is one major way of providing cavitation sensitivity to minimize the cavitation possibility on propeller blades. And leading edge contours also, if you carefully control, you will be able to minimize cavitation. And also, it has, as you know, cavitation also has an added advantage of reduced high hull vibration, and also the structural fatigue loads and all can be reduced, and much more efficient structure can be designed with this. Next slide. So this I already covered. Last sentences may be valid for you. Large diameter, just previous, large diameter slow turning propellers will produce less noise in general. So that is one. Next. So this is another method. It has been well proven. I found it in a journal paper actually. This is the vortex generators fitted on a tanker. That's what is seen here. If these are fitted carefully based on the hydrodynamic motor testing and all. So if you fit it, these vortex generators will deflect the flow upwards. And that is found to help in minimizing the non-uniformity in the wake towards the propeller. So that's what is done here. It's on a tanker, which will reduce the non-uniformity of wake and reduce cavitation. Next slide. And so I have covered the propeller part. Coming to another part called the machinery, second part. Second major source of noise and vibration in ships is the machinery-induced noise. Basically, this happens through three major parts. You can see there is a machinery like an engine fitted there, and it's fitted on some mounts. You can see here, fitted on the structure. So this noise propagation into the water, under radiated noise in water, has got three major paths. One is the first structure-borne path. This is a major path. You can see the vibration will get directly transmitted into the hull. Hull will vibrate, and that will create noise into the sea. Second path is the airborne, second structure-borne path. That is nothing but the noise will come and hit on the structure, and then that structure will vibrate. That's second structure-borne path. And third one is the directly airborne path that is coming to the water actually. Excellent. So airborne path, this is mostly relevant only when the machinery compartment is directly adjacent to the water, and noise impinges directly on the hull, and so there is a transmission loss taking place, noise transmission loss across the hull plating. And the plating thickness and stiffener spacing, if you can modify that, you can highly help to reduce the vibration and minimize the transmitted noise into the sea. And another major option is if you have freedom to keep the noisy machinery, whichever machinery is creating a lot of noise, keep it in the well inside the, so that it's not directly adjacent to the sea. So that is another, placing noisy machinery in the inner compartment. Next slide. And this is the first structure-borne path. I told this is coming through the foundations and directly transmitted into the hull, and hull vibrates. This is hard mounted. There are two types of machineries. You can, it can be mounted. Most of the things are either, here you can see some mounts taking place. These are typically called vibration isolation mounts or shock mounts in submarines. So they will try to, they are resilient mounts made of rubber and some compliant material. So they will vibrate and minimize the radiated noise, vibration and associated radiated noise. There are some problems with that. This is mostly used in all ships, but in a congested area, like in a submarine or where the area is very congested, don't have even millimeter kind of level tolerance is available, then if this is vibrating, it will create a lot of problems. It may create interference with the other structures, or this may not be always possible in a propeller shaft and all, because shaft is turning, and then you cannot have this compliant mounts there always, because it is a rotating system. So there, but still it is fitted on almost all kind of mountings wherever it is possible, because it will have major impact in reducing the underwater radiated noise and vibration in the ships actually. This is a typical example of a vibration mount. And another major point is this: its frequency of operation should be very carefully studied. If it's creating resonant vibration, then there is nothing like that. Everything will go into a problem if there is a resonant vibration. So these mounts should be very carefully designed to avoid resonance. Next. And in many of the things, many of the ships and submarines and all, thermal and fire insulation materials are there. So they are also a major source of absorption of sound. So they can also be used. Reductions up to 10 dB can be achieved depending upon the frequency range and with greater effectiveness. Next slide. And damping tiles. This is used, if you have looked at a submarine, you might have seen some photographs. It's available in internet and all. There will be a big tile, black color tile fitted, very thick, almost 50 mm to 60 mm thick tiles are there fitted all around the submarine actually, because that is to reduce the radiated noise. So these are typically damping treatments done. But these are very heavy actually. They are damping because of the energy dissipation effects. So that means these are very heavy things, and weight increase. There will be a lot of weight increase will be there. But wherever this is major importance, you have to sacrifice that and we have to go for this. But another kind of damping treatment is spray on. It's like a paint. You can apply spray paint kind of damping materials on the hull. But if that spray paint also, each spray layer will be 1 mm. We have to use multiple layers so that the layer thickness built to 40 mm or 50 mm and all. And again, still it is a very heavy kind of material finally. But that also can be used wherever it is there. It is useful. Yes, next. This is what I was telling, the damping treatments. There are these are some of the disadvantages. Materials are very dense and weight increase can be significant. And with respect to fire ratings, you may not be able to use it always in an accommodation area, because when it is the fire is there, this can create very dangerous smokes. So that also sometimes it is not very useful in those areas. Next. And machinery induced noise, one of the most useful method for reducing machinery noise is selection of equipment with inherently low noise and vibration. There are for this you can see the vibration data measured on measured for 2 isolation mounted machineries of the same power and RPM ratings. There are everything is same, but 2 brands of machineries. But you can see the difference in that noise level or vibration level between these two. Again, here you can see 20 dB and all. There's a big difference in there. So when you select the machinery or equipment, that is a first method of most effective method of reducing noise and vibration by selecting the appropriate machinery. And reciprocating and type of machinery. There are different types. So if you are selecting a pump, there can be different methods. So reciprocating pumps, they are more vibroactive than screw pumps. So these are all small things, but cumulatively it will greatly add to the net vibration or noise levels in a ship. Next. And I have completed the propeller noise and the other noise, machinery noise. Another kind of noise that occur in ships and submarines is the flow-induced noise. When the turbulent boundary layer flow passed over a underwater object or ship hull, there are boundary layer is filled with there are a lot of pressure fluctuations taking place in the boundary layer. So typically this is the, you can see this is the wall pressure recorded, or is a simulated wall pressure with respect to time. So very minute kind of thing taking place, or this at very small speed, that's why 1.5 Pascal and all you are getting. But at 20 knots and all, this can be quite significant. And these turbulent boundary layer pressure fluctuation can excite the wall. For example, this is a submarine hull again. You can see when this is excited, the plate will have a response, respond to that. That vibration will get transmitted to the interior, and wherever your acoustic equipment is there, that's performance will be severely affected. So, and also it is also very important in the next slide. This feature is also important in the these areas also, in civilian commercial areas where we have the aircraft. These turbulent boundary layer pressure fluctuations excite the hull, and that is both way transmitted. If it is transmitted to the interior, there will be large noise inside for the crew, and also if, this radiated noise to the outer, it will be very disruptive to the population in the neighborhood, because large noise will be generated. So here this is an area where large number of research papers and a lot of research has gone into it on this classification of this pressure fluctuation induced noise and vibration. And again, this is applicable in the submarines. And it is also there in the cars and all, where again the same phenomenon are there, transport cars and all. And the last figure is sonar tubes, where we have again these hydrophones and all are there, which are again disturbed by this flow-induced noise and vibration. This is one method of estimating this, which sir knows. Sir was my PhD guide, and this was done under sir's thing. This work was done by me only, where we can estimate the pressure fluctuation over the tubes and calculate this kind of wave number frequency spectrum can be generated for the wall pressure fluctuation. This is typically the sonar dome of a ship. This is not a bulbous bow. You might have seen some ships which are research ships dealing with acoustic research, where there is a bow at the and you can see this this acoustic transducer actually. It's called bow mounted sonar, which is looking for presence of submarines under in the sea and all. So this phenomena is very significant here when this dome wall, you can see the sonar dome wall, will again get excited, and this noise and vibration will get transmitted to the interior of the and again it will create a lot of so here also baffles, all these tiles, all these things are fitted to mitigate this noise actually. So impact on cost, there are, to reduce the URN is a design cost, material procurement, as I told, isolation mounts, flexible connections, insulation material, these are all, again, it has got its own cost impacts, and material installation, its own cost impact. And also on space and weight, we have the additional height of mounts wherever it may not be possible, ships are congested spaces. So if you bring in additional mounts and supporting structures and all, they will take, it will have its impact on space and weight. And damping treatments, all those things will significantly increase the weight. So, but URN reductions of the order of 3 to 10 dB over existing levels are possible. Typically, it's a typical estimate of 1% of the ship cost it can come if you try to reduce the 3 to 10 dB level, the noise reduction. This is actually some of the existing regulations regarding that. ICES is the International Council for Exploration of the Seas, mainly concerned with the fisheries research, where we have they have stipulated the permitted radiated noise levels from a ship. So that's what is seen here. You can see this is the ICES curve, which typically says from frequency in the range of up to this 10 kilohertz and all. This is the 135 dB and all. This is the permitted curve of the radiated noise from a ship, which is as per ICES. So typically nowadays the ship owners are moving towards, now they are more aware of the green solutions and all to reduce the environmental noise pollution and to be more friendly towards marine animals. Many ships are there which are now trying to comply with this regulation, but as of now it is not a statutory regulation, but this kind of recommendations are there. You can see here, yeah, this is one ship which has achieved. This is ship data. It's a measured data of a ship which has complied with this ICES regulations. That's what is seen here. Next. There are many classification societies having this quiet ship notation. For example, DNV is having its own silent class is there, which the ship which I mentioned, which GRC is going to build, is as per this DNV silent class. This is a curve taken from the DNV silent class. Again, it stipulates frequency versus dB levels permitted in a ship actually. And it is also made in line with the ICES curve, which I showed in the previous slide. DNV has mostly adopted from that regulations, and DNV has got actually these different classes are there, like silent A, silent S, fisheries, R for research, and E for environmental research and all. So for this is what the curve which I have given is from the DNV silent class R curve. Similar curves are there for the other classes also. Next. This is my last slide, how to measure this. So DNV silent class, this is taken from the DNV measurement scheme for the, so once the ship is built as per DNV silent class, then once the ship is built, they have to do this exercise. That means this is the hydrophone which is moved in the sea somewhere with a weight and all, where is a boy sing and all. And once the hydrophone is moved, the ship will take a sail past the hydrophone at a specified distances and all. And this noise is recorded, and it is seen that this noise is less than the class stipulated noise. That's how it is finally measured. And then the class certificate is given that this is complying with DNV silent class. So I stop here. Thank you very much for a person have a patient listening.
Okay, thank you, Dr. Roni. Very informative presentation. Any questions from the audience?
So thank you very much for your nice presentation. You said noise is generated by propeller
Yes.
rotation, and you make some designs to avoid the noise.
Yes, yes. There are
okay.
various methods
So-
available to minimize the noise
Okay.
from
Is there any method of coating the
yes.
propeller so that noise?
Yes, yes, yes. There are many research papers are available.
Available.
They are calling it compliant coatings, which are found useful for reducing the noise from propeller. It is available. A lot of research papers are there on that.
Okay.
In fact, these are mostly these.
Are there any research currently going on in
Yes, yes,
NPOL,
yes, yes,
NPOL
yes.
regarding this?
NPOL, some
coating?
minor level it is there, not in a major area.
What are the
but-
methods which are adapted to test the coating?
So far, it is not. It is a highly coming out area only. It has
Okay.
not gone into advanced area. There are many research papers. I am not from this area. There is a material science group in NPL which is working on this actually. Sir, you may be knowing one that Ramesh Kumar and Dr.
Oh,
Narma.
they are working
Yeah,
on
they are
this.
working on the area, but it is in a very nascent stage actually. It has not
Okay.
come to. But there are many research papers available which talk about this compliant coating material for reducing. And another thing is which most of these research are taking place in the defense area. So no information is actually available. What is this material which they are using?
Yeah,
Somehow
that's
they are able
correct.
to manage, but that information is not passed.
Ronnie, what are the efforts in India to reduce propeller radiated noise? I'll ask many linked questions. Whether India is capable of computing the radiated noise from propellers, whether when we design propellers, thrusters for our ship, before fitting it, we can do any tests or have any level of confidence that we will be able to achieve these low levels of noise.
That's what, sir. As of now, in India, there is no effort has been made or no ship is also built which is focusing on the underwater radiated noise. So this ship which I mentioned is the first time somebody is going to make a ship which is complying with this silent class. So far, all propeller design has been made with the idea of designing it without cavitation. So that thrust and all those things are available. But noise point of view, nobody has looked at it actually.
But propellers normally should not cavitate,
Especially
especially.
on speed, sir. Speed it will depend upon.
Okay.
The speed increase at low speed it will not cavitate.
Uh,
But once that's why we go for at high speeds and all, especially naval ships and all, go for water jet propulsion because propeller inevitably cavitate. If it crosses some 20 knot speed and all, it's a brink of cavitation.
Okay.
And then
So you have specified radiated noise levels. Whether the speed of the ship is also specified in that chart?
that DNV specifies these tests are to be done at 11 knots. 11 knots.
Okay.
11 knots is somehow they have made the standard.
Fine.
And it is adopted by ICS also.
So your requirement is also at 11 knots.
My ship is 12 knots,
Hmm.
but DNV, once I said DNV class, finally they'll design it for 11 knots.
Okay. Recently, we did computation of radiated noise from propellers, and we saw characteristics in the radiated noise that we don't see in other papers.
Okay.
We are expecting certain noise characteristics from the propeller, and we can see that in our computation, but I don't see it in other published papers.
Okay.
So if you're interested, we can do some calculations. You give us propeller geometry, we can.
Estimate that.
Yeah.
Yes. There are the package like ANSYS, I think Fluent,
Yeah.
even Fluent can do this.
Sure,
If
it
you-
can do it, but the
Yes.
people don't know how to use it properly. So everybody uses it, publishes
yes,
it, but that it does not have the characteristics it is supposed to have.
But the thing is, we should have something to compare. If you do something in Fluent, definitely some result will come out, but nobody knows whether it is correct or not.
Yeah.
So if you should have field data, somebody has measured it. So then it can be much like it. Recently, I had interaction with one DNV surveyor who came here to our lab. So he was telling DNV, these measurements are, they are well established and they are quite capable to do these measurements.
Measurement of what?
Radiated noise.
From the
Ships.
propeller or the whole
No,
ship?
no, that measurement will be complete.
Yeah.
Yes,
So,
okay.
but it's good to test subsystems before building the ship and
But
putting everything on the
there
ship.
should be a means to do that,
Yeah.
sir. I think you may be aware, sir, in NPL that cavitation meter, one project was there.
Hmm.
They are specifically looking at propeller cavitation aspects and it's a small project.
So we know how to create a propeller given cylindrical section details. We know how to compute the radiated noise. If you are interested, we can do something.
Okay.
Yeah, okay, if no more questions, we'll wind up. Thank you for the presentation.
Yeah.
And I think
Thank you, sir. I now invite our session chair, Professor Dr. P. Krishnagurti, to present Dr. Roni Francis with a token of appreciation and a certificate. Sir, please. With this, we conclude our section. A heartfelt thank you to all the speakers and the session chair for sharing their valuable knowledge and expertise in the field of marine structures and artificial intelligence. I now invite Dr. Professor A. Madhyadagan to present a memento to Professor Dr. P. Krishnagurti as a token of appreciation for his guidance throughout the section. High tea has been arranged for everyone outside. Kindly enjoy yourself and join with us tomorrow at 9:30 a.m. for the continuation of the seminar. Thank you.